2.1 Exponential and Logarithmic Functions. Part 2. Defining logarithms, applying logarithmic properties, and graphing logarithmic functions. Southwestern College, Professor Maria Olivas. Section 2.1 Exponential and Logarithmic Functions. Objectives. Define general logarithmic functions and their properties. Define the natural logarithmic function. Apply properties of logarithms to rewrite expressions and solve equations. And graph logarithmic functions. 1. The general logarithmic function. A logarithmic function has the form log base b of x equals y if and only if b raised to the y power equals x, as long as b is greater than 0 and b is not equal to 1. So I am underlining the words logarithmic function. I am going to put a box around where it says log base b of x equals y. I'm pointing an arrow at the IFF, which stands for if and only if, and I'm writing those words above it. I'm circling the part that says b raised to the y power equals x. So these are key parts here for this definition of what is a logarithmic function. I'm going to write up here in the right hand side of the screen log base b of x equals y. I'm going to circle the base b, and I'm pointing an arrow at it, and I'm writing down the word base. And then I'm going to point an arrow in a circular fashion going counterclockwise from the b to the y. And I'm writing underneath the arrow raised to this power. So it's going to be b raised to this power, which is the y power, is going to be equal to, I'm now drawing an arrow from the y to the x, again going in that circular fashion, counterclockwise. I'm going to rewrite it now in exponential form. So this is going to be represented as b raised to the y equals x. And this is what I like to do in order to remember how to rewrite a logarithm in exponential form. Logarithmic functions are the inverses of exponential functions. So with inverses, remember that when you have a function and it contains the ordered pair a comma b, then its inverse will contain the ordered pair b comma a. So we have two common bases when working with logarithmic functions. One, base 10, which we call the common log, and we represent that by writing y equals log base 10 of x, and then I drew an arrow pointing to the right. This means the same thing as y equals log x. And very commonly, we do not write in that base 10, and it is just known that when you write y equals log x, it is a base 10 common log. Number 2, base e, the natural log. We write this as y equals log base e of x, but more commonly this is written as, I drew an arrow pointing to the right, y equals the natural log of x, or we can also write that as y equals ln x. Inside parentheses, I'm writing down the words natural logarithm. Example 1, graph f of x equals log base 2 of x. So to begin this first problem, I'm going to rewrite the equation so that instead of an f of x, we're going to see the y written there. And that's because my goal is to rewrite this in exponential form, and I would like to see the y so that way it's easier when I rewrite this in exponential form for me to write in a y for that exponent. So let's write this as y equals log base 2 of x. Now when I rewrite this in exponential form, I'm going to circle my base. I'm going to draw an arrow going across to the other side of the equal sign in a circular motion. In this case, we're going clockwise. So it's going to be 2 raised to the y power is going to be equal to x. Now I'm highlighting where it says log base b of x in the definition part where I rewrote it up here. And I'm showing you that here the log base 2 of x is on the right hand side rather than on the left hand side where I had originally written it. But that's okay. We can still rewrite this in exponential form. If you need to rewrite it so that the log base 2 of x is on the left hand side, then do that. So that's what I'm doing right underneath it. I wrote log base 2 of x equals y, and if that's easier easier for you to rewrite this in exponential form, then do it that way. So here, if I do it that way, I have once again circled the 2, I have drawn an arrow, this time going counterclockwise to the y, and then another arrow pointing to the x, and I have rewritten it as 2 raised to the y equals x. On the left-hand side, I have drawn a 2-column table. Under the y's, I am choosing values to substitute for y, which is -2, -1, 0, 1, and 2. We normally choose values for the x, but this time we're going to choose for the y because our y value is the one that's in the exponent part, and it's easier to choose those values. So I'm going to go ahead and write these in here. We got 2 raised to the -2 power, which is equal to 1 over 2 squared, which equals 1/4. So I'm going to write that next to the x. And then for y equal to -1, we're going to get x equal to 1/2. Y equal to 0, we're going to get 1. Y equal to 1, we're going to get x equal to 2. Y equal to 2, we're going to get x equal to 4. So for my table of values, I've got the ordered pairs 1/4, -2, 1/2, -1, 1, 0, 2, 1, 4, 2. I am now going to draw my coordinate plane on the right-hand side of my screen here. So I have drawn on my vertical axis, I'm drawing my tick marks. My tick marks are going to go from -2 to 2 by a scale of 1. The tick marks on the horizontal axis for my x-axis are going to go from 0 to 4 by a scale of 1. I've labeled my x-axis with an x, and I've labeled my y-axis with an f of x. Now I'm going to go ahead and plot my points. So let's go ahead and start by plotting the points here. And I've also drawn little tick marks here to represent the values, or tick marks for the values of 1/4 and 1/2. So I've plotted the points 1/4, -2, 1/2, -1, 1, 0, 2, 1, 4, 2. I'm going to draw a curve going through all of these points. I missed one of my points, so I'm erasing it and drawing it so it looks like it lands on my curve. I have extended my curve to the edges of my coordinate plane, and I am drawing arrows on the ends of my function. I'm labeling each one of my points with its corresponding ordered pair. So now that I have labeled each one of my points with its corresponding ordered pair, I am also labeling the function with its equation, which is f of x equals log base 2 of x. Now let's find the domain and the range of this function. Let's start off with the domain. So here for this particular function, there is a vertical asymptote. So that vertical asymptote is going to be right on top of the y-axis. And the equation of that vertical asymptote is going to be x equal to 0. So this means that our x values will be strictly positive. The domain will be the open interval from 0 to infinity, or the set of all x such that x is strictly greater than 0. The range is going to be all real numbers, so that's going to be the open interval from -infinity to infinity, or the set of all y such that y is an element of the set of real numbers. All right, let's move on to example 2. Write an equivalent exponential equation. So for 2a, it says the log base 3 of 81 equals 4. I'm going to rewrite that. So I'm going to rewrite log base 3 of 81 equals 4. I'm going to circle the 3. I'm going to draw my circular motion going counterclockwise, where it 3 points at the 4, and then the 4 points at the 81. So that to me represents 3 raised to the 4th power equals 81. I'm going to box that in. For 2b, it says log base 4 of 16 equals 2. I'm just going to rewrite that whole logarithm. I'm going to circle the 4, which is the base, point it towards the 2, and then point the 2 towards the 16, which to me reads as 4 raised to the 2nd power equals 16, and I'm going to box that in. And that's going to be our answer for 2b. 2c says log base e of y equals t. So once again, here, I'm going to circle the E, I'm going to point it at the T, and I'm going to point from the T to the Y. This is going to read as E raised to the T power is going to equal Y. Now this also could have been rewritten as the way I wrote it at the top, and I rewrote this here so you could see that another way that this problem could have been written was the natural log, or ln, of y equals t. And they mean the same thing. So I've gone ahead and written my answer, e raised to the t power equals y, and I have boxed that in. 2d says log base 5 of, open up a set of parentheses, 1 over 125, close the parentheses, equals -3. I have circled the 5, I have pointed it to the -3, and then I pointed from the -3 to the 1 over 125, and to me that reads as 5 raised to the -3 power equals 1 over 125. Example 3. Solve for the missing variable. So 3a says log base 3 of x equals -4. So I'm going to rewrite this. First I'm going to circle the 3, point it at the -4, and then from the -4 I'm going to point to the x, and that reads to me as 3 raised to the -4 power equals x. Since I'm trying to solve for x, I'm going to simplify 3 raised to the -4, so I'm going to rewrite this as x equals 1 over 3 to the 4th, which equals 1 over 81. So x is equal to 1 over 81, or another way we could write this as the solution set with a pair of braces around it of 1 over 81. And we can write it this way because we are solving for a missing variable in an equation. And we're going to go ahead and box that answer in. 3b says log base 4 of 1 equals x. I'm going to circle the 4 in the base, and then I'm going to point it at the x, and then from the x I'm going to point to the 1. And to me that reads as 4 raised to the x power equals 1. So the only thing that I could raise 4 to make it equal to 1 is a 0. So I'm going to rewrite that as 4 raised to the 0 power equals 1. So that means x has to equal 0, or the solution set containing 0. I'm going to box that in. Example 4. Evaluate each logarithm without a calculator. So 4a says log base 2 of 32, and it doesn't say that it equals x, but I am going to write down that it equals x in order to help me rewrite this in exponential form. So I'm going to write down log base 2 of 32 equals x. I'm adding the equals x. I'm going to circle the 2, point it at the x, and then from the x I'm going to point to the 32, and to me that would read as 2 raised to the x power equals 32. Well, if I were to factor out 32, in case I didn't happen to know that 2 raised to the 5th was 32, I could factor it out, get its prime factorization, and the prime factorization would actually give me 5 factors of 2. So that means x has to be equal to 5. I'm going to highlight the directions here for example 4 and example 3, and I want you to notice the difference between these two sets of directions. So notice here for example 4, I am highlighting where it says evaluate each logarithm without a calculator, and I am boxing in the words evaluate each logarithm. Let's compare the example 3 directions. Example 3 said, and I'm going to highlight these words as well, solve for the missing variable, and I'm going to box in the word solve. These instructions are different for both of these problems. I'm going to draw a large right curly bracket on the right hand side, extending the entire vertical length of the example 3 problem, and I'm going to write down the word solving equations next to it. And I'm going to do here the same for example 4. I'm going to draw a large curly bracket on the right hand side, and I'm going to write down the words evaluating logarithms so you can notice the difference between these two problems. So even though example 4a did not have an x originally, I chose to put the x in to make it look like as if I were solving an equation, but in reality I wasn't solving an equation. So when I do write this answer at the end, notice how I'm writing this answer differently from the answers from 3a and 3b. So I'm writing this as log base 2 of 32 equals 5, and I'm just going to box in the 5. That's what I get when I evaluate the logarithm. I am not writing x equals 5. I am not writing the solution set containing 5 because there was no x to begin with. I'm pointing an arrow here at the x that was above that I wrote in, and I'm writing down the words next to it. This x was not part of the problem. And I also drew another arrow writing that I wrote this I wrote this x in. Since I chose to write this x in, it's not part of the original problem. I don't want to write my answer as a solution set. Okay, just want to make sure I make that very clear. I'm going to put in a vertical line segment divider to separate the work from 4a and 4b. Example 4b, log of 1/10. So I'm going to rewrite this as the log base 10 of, open up a set of parentheses, 1 over 10, close the parentheses, and then once again, I'm going to write it equals x because that's going to make it easier for me to write this in exponential form. I'm going to circle the 10 in the base, I'm going to point it at the x, and then from the x, I'm going to point an arrow pointing towards the 1/10. So to me, this reads as 10 to the x power equals 1/10. So the only thing I could raise 10 to make it equal to 1/10 would be -1. So I'm going to write my answer as log of 1/10 equals -1 and box in the -1. So remember, I don't have to write in that base 10. When you don't write the base 10, we know it's a common log and we know automatically that the base is supposed to be 10. So I am going to draw in a vertical line segment divider to separate the work between 4b and 4c. I am also going to go ahead and erase the big curly bracket I drew on the right hand side and the words that I wrote about evaluating logarithms so that I have enough space to show my work for problem 4c. Example 4c, log base 5 of 1. I'm going to rewrite this as log base 5 of 1 equals x, so I can rewrite it in exponential form. I'm going to circle the 5, point it at the x, and then from the x, I'm going to point to the 1. To me, this reads as 5 raised to the x power equals 1. The only thing I could raise 5 to make it equal to 1 is a 0. So I'm going to rewrite over here on the right, 5 raised to the 0 power equals 1. And my answer is going to be log base 5 of 1 equals 0. I'm going to box in that 0. Properties of logarithms. Inside parentheses, we have a comma b are strictly greater than 0. And then we have, this is true for all logarithms of any base, written right next to that. Number 1, the natural log of 1 equals 0. So this means the same thing as log base e of 1 equals 0. And of course, if you were to imagine this, the only way e raised to any power is going to be equal to a 1 is going to be if you raise it to the 0 power. Number 2, the natural log of e is going to be equal to, well, let me rewrite this first as log base e of e. So it's going to be equal to, obviously here, 1, because if I raise e to the first power, then it's going to be equal to itself. So we're going to write here that the natural log of e is equal to 1. In that case, a more general form of writing this would be the log base a of a is equal to 1. If the base is equal to the number that you're taking the log of, then this is going to be equal to the number 1. Number 3, the natural log of e raised to the x is going to be equal to, yes, x. And then comma, here we have e raised to the natural log of x is going to be equal to x. These are called inverse function properties. And a more general form for this would be the log base a of a raised to the x is equal to x, or a raised to the log base a of x is equal to x. Number 4, this property represents that the log of a product is equal to the sum of the logs. So the natural log of the product a times b is going to be equal to the natural log of a plus the natural log of b. Now I'm going to take the work that I did above here for the inverse function properties. I'm going to circle it and I'm going to just raise it up so I have more space to write. And I'm going to draw a vertical line segment between my properties here for properties 4, 5, and 6 so I can show you the general form of these properties. So the general form for property number 4 is going to be the log base m of the product a times b is going to be equal to the log base m of a plus the log base m of b. And once again, that represents that the log of a product is equal to the sum of the logs. Let's go on to property number 5. Property number 5 is going to represent that the log of a quotient is the difference of the logs. So let's begin by representing the property that has the natural log in it. So for number 5, this one states the natural log of, we're going to open up a set of parentheses here, we're going to have the quotient a divided by b, and then close the parentheses. That's going to be equal to the natural log of a minus the natural log of b. And the general one for that one is going to be the log base m of the quotient a divided by b is equal to the log base m of a minus the log base m of b. Now, property number 6. This property states that the natural log of a raised to the n power will be equal to n times the natural log of a. And the general form of that is going to be the log base m of a raised to the nth power is going to be equal to n times the log base m of a. And that states that the exponent on the argument is the coefficient of the log. Example number 5, expand each logarithmic expression. 5a. The natural log of, open up a set of parentheses, e times the square root of 3x plus 2, and then we close the parentheses. I'm going to go ahead and rewrite this. So I'm going to rewrite the natural log of, open up a set of parentheses, e times, and I'm actually going to represent that times symbol, times the square root of 3x plus 2, and then close the parentheses. Now this represents here that the log of a product is going to be equal to the sum of the logs. So I'm going to rewrite it as the natural log of e plus the natural log of, open up a set of parentheses, 3x plus 2, close the parentheses, and I'm going to raise it to the 1/2 power. So I'm going to rewrite that square root as a fractional exponent. Our next line is going to be the natural log of e will turn into a 1 plus 1/2 times the natural log of, open up a set of parentheses, 3x plus 2, close the parentheses, and we're going to go ahead and box that in. That's going to represent our answer. And that last property we used there was the exponent on the argument is equal to the coefficient of the log. So that's why I rewrote that 1/2 in front of that natural log. I'm going to go ahead and draw a vertical line segment here to separate the work between example 5a and 5b. So for b, this states that the natural log of, open up a set of parentheses, here we have a quotient inside the parentheses, we have x times y squared in the numerator all over the cube root of z, and then we can close the parentheses. So this is going to represent that the log of a quotient is equal to the difference of the logs. So I'm going to rewrite this as being equal to the natural log of, we're going to open up a set of parentheses, x times y squared, close the parentheses, minus the natural log of, open up a set of parentheses, the cube root of z, close the parentheses. This is going to be equal to the natural log of x plus the natural log of y squared. There we're using that the log of a product is equal to the sum of the logs, minus the natural log of z raised to the 1/3 power. I'm just writing the cube root as a fractional exponent. And then this is going to be equal to the natural log of x plus 2 times the natural log of y minus 1/3 times the natural log of z. And in those two last logarithms, we used the exponent on the argument is equal to the coefficient of the log, and we just rewrote that exponent that was in our argument, and we wrote it out in front as the coefficient of that log. Let's go ahead and box in that answer. Example 6. Condense the logarithmic expression, the natural log of x minus 3 times the natural log of y plus the natural log of 2. Condensing is the reverse process of expanding. Now I'm going to highlight the minus sign in front of the 3 natural log of y. This represents a negative exponent. Remember that the coefficient in front of the logarithm is an exponent to the argument. Just as in example 5b, I am highlighting the minus sign, and I'm highlighting the cube root of z, and I'm highlighting that negative 1/3, that was the coefficient in the end answer. And if you notice, you put that all together, that all represented a negative exponent for that z, that negative 1/3, which could also mean the cube root of z. If you notice here, back in example 6, I highlighted in green the plus sign in front of the natural log of 2. This means that the 2 has a positive 1 exponent, which means it's ultimately going to be written in the numerator once I condense this logarithmic expression into a single logarithmic expression. So that's what it means. If I look at the first logarithmic expression here, that positive natural log of x, it also has an imaginary plus sign in front of it, which means that x has an exponent of positive 1, which means the x will ultimately end up in the numerator of my logarithmic expression once I finish condensing it into a single logarithmic expression. So when we are condensing logarithmic expressions, you need to be very careful about the order in which you do this. I am going to focus on anything that has the power rule being applied to it first. So for example, where it says that minus 3 natural log of y, I want to apply the power rule. Now it's up to you whether you want to write that as natural log of y raised to the negative 3 or, minus the natural log of y raised to the third. You just need to be careful that you don't forget that that actually represents a negative exponent. Once you take care of the exponent part, you can go ahead and just focus going from left to right. So for my next line here, I'm just going to go ahead and rewrite this as the natural log of x minus natural log of y raised to the third power, and then plus the natural log of 2. Notice I did not put the negative exponent in because I want to apply the properties we had just mentioned earlier. So I'm going to write this as the natural log of x divided by y cubed, and then plus the natural log of 2. And this is going to be equal to the natural log of, open up a set of parentheses, x over y cubed times 2, and I'm going to write that as 2 over 1 and then close the parentheses. This is going to be equal to the natural log of 2x over y cubed, and I'm just going to put that whole quotient inside a set of parentheses so it's clear that we're taking the logarithm of that entire quotient, and I'm just going to box that answer in. Example 7. Simplify each expression. And inside parentheses it says no calculator. A, natural log of e raised to the third power. This is going to be equal to 3 times the natural log of e. Natural log of e is just 1, so this is going to be equal to 3 times 1, which is just going to be equal to 3. Let's go ahead and box that answer in. Let's go on to example 7b. Example 7b says the natural log of, we're going to open up a set of parentheses here, 1 over the square root of e, and then close the parentheses. And this is equal to the natural log of 1 over e raised to the 1/2 power. I've just rewritten the square root of e as e raised to the 1/2 power in the denominator of that fraction. And this is going to be equal to the natural log of, I'm going to write this inside a set of parentheses, e raised to the negative 1/2 power, close the parentheses, equals the same thing as negative 1/2 times the natural log of e, which would be equal to negative 1/2 times 1, which is just equal to negative 1/2, and I'm going to go ahead and box that answer in. Example 8. Graph f of x equals e raised to the x power, and we also have g of x equals the natural log of x. And I'm going to write in on the same coordinate plane. So we want to graph two functions on the same plane, f of x here and g of x. In order to do this, we need to find some ordered pairs. So I'm going to create a table of values. It's going to be a 2-column table. I have drawn the table here. I lassoed it and I moved it slightly down to the lower left. I'm writing f of x equals e raised to the x above this table, and I have labeled the left-hand side of the table for my x values and the right-hand side for my f of x values. I'm going to copy and paste another one of these tables on here so that I don't have to draw another table for my g of x function. And I have pasted it to the right-hand side of my first table that I drew. I'm going to erase where it says f of x in the second table that I just pasted, and I'm also going to erase the x. At the top of the table, for the second table, I'm going to write g of x equals natural log of x, and I'm going to write x at the upper left-hand corner of this two-column table, and g of x on the upper right-hand corner. I'm going to erase the page number that's at the bottom so I have more space to write. For the first f of x equals e raised to the x, for the x values, I'm going to choose -2, -1, 0, 1, and 2. What I'm going to do now is I'm going to rewrite the g of x equals natural log of x in exponential form. First, I'm going to write it. Actually, I don't have enough space. I'm going to lasso the work I had here for my previous example, shrink it, and move it upwards slightly so I have more space to write. Now, what I'm going to do is I'm going to rewrite that equation as y equals log base e of x. And I'm rewriting this as e raised to the y power equals x. I've circled the e, pointed it to the y, and then pointed it to the x to remind me to write it as e raised to the y equals x. If you can see and you compare this equation with f of x equals e raised to the x, these are inverses of each other. So what I'm going to do is I'm just going to go ahead and switch the values here for my x and y columns. For my g of x, I'm going to choose -2, -1, 0, 1, and 2 because that's what I chose for my x values for f of x. And for f of x, I'm going to go ahead and figure these out by plugging these in, and I'm going to get, for f of -2, we're going to get 1 over e squared. For f of -1, we're going to get 1 over e. For f of 0, we're going to get 1. For f of 1, we're going to get e. For f of 2, we're going to get e squared. And because we already mentioned that these are inverse functions of each other, I'm just going to copy these values down under the x column for g of x. So since g of x is the inverse of f of x, the ordered pairs for g of x are going to be the following: 1 over e squared, comma, -2, 1 over e, comma, -1, 1, comma, 0, e, comma, 1, e squared, comma, 2. And then for the approximations for these, in order to allow us to graph these and plot these points, I'm going to write down the following approximations. I'm going to write them down under the f of x column. So 1 over e squared is approximately 0.135. 1 over e is approximately 0.368. 1 is just going to be 1. E is approximately 2.718. And e squared is approximately 7.389. I have also written little approximation symbols pointing towards the x values in the g of x two-column table because they are the same approximations for those values. I'm going to go ahead and draw my coordinate plane on the right-hand side of the screen. We're going to begin by drawing the tick marks on the y-axis. We're going to start off on the positive side of the y-axis by going from 0 to 8 by a scale of 1. Then we're going to do the positive side of the x-axis, going from 0 to 8 by a scale of 1. Then the negative side of the y-axis, going from 0 to -8 by a scale of 1. And lastly, we're going to do the negative side of the x-axis, going from 0 to -8 by a scale of 1. Now I'm ready to start plotting my points. So I'm going to go ahead and start off by plotting the points for f of x is equal to e raised to the x power. We're going to start off with -2, 0.135, and then we're going to do -1, 0.368, 0, 1, and then 1, e, which is 2.718, and then 2, e squared, which is 7.389. Now that I have drawn my points, I'm going to connect these points with a curve. I'm going to extend the curve to the ends of my coordinate plane. I'm going to draw arrows on the ends of my function. I'm going to label my function with its equation f of x equals e raised to the x power. So I normally label my ordered pairs immediately, but I'm going to hold off on labeling the ordered pairs. I want to graph g of x first, and then after I finish graphing g of x, then I will label each one of these ordered pairs just to make sure I have enough space. So let's go ahead and start plotting the points for g of x. We'll begin with the first ordered pair. So it's going to be the 0.135, -2, then 0.368, -1, then 1, 0, and then e, 1, which is 2.718, 1, and then e squared, 2, which is 7.389, 2. I will connect my points with a curve. I will extend the curve to the edges of my coordinate plane. I will draw arrows on the ends of my function, and I will also label this function with its equation g of x equals the natural log of x. Now you can tell that these are inverse functions, because if I draw the line y equal to x, you can see that these two functions are mirror images of one another. So I am drawing the line y equal to x here on the graph as a dashed red line, and I am labeling that line with the equation y equal to x. Now, I was not asked to do this in example 8. I was just asked to graph f of x equals e raised to the x power and g of x equals the natural log of x, but I chose to graph this line so that you could see that these two functions are actually inverses of each other. I am now labeling each one of these points. So I have started off by labeling the points that are on the function f of x equals e raised to the x power with their ordered pairs. And now I'm going to label g of x equals natural log of x with the ordered pairs for each of those points. So this is for the point 0.135 comma negative 2, or 1 over e squared comma negative 2, and then 1 over e comma negative 1, and then 1 comma 0, and then here we have e comma 1, and last but not least e squared comma 2. So I have labeled all of those ordered pairs as well. Okay, now we're ready to move on. So let's go ahead and move on to our section 2 for this video. Section 2 for this video is going to be on solving exponential equations. Remember, logarithms and exponents represent inverse operations. That means you can use logarithms to solve exponential equations and exponents to solve logarithmic equations. Examples. Solve each exponential equation. Number 9, e raised to the power 2x minus 1 equals 5. So here, if you notice, our variable is in the exponent. We need to make sure we bring down that variable. So I'm going to take the natural log of both sides of this equation. We're going to have here the natural log of e raised to the power 2x minus 1 equals the natural log of 5. Now I can use the power rule for logarithms. Let's bring the exponent down in front of the log and multiply it to the ln of e. So we get the quantity, we're going to open up a set of parentheses, 2x minus 1, close the parentheses, times the natural log of e equals the natural log of 5. So this will be the quantity 2x minus 1 times 1, because the natural log of e is 1, is going to be equal to the natural log of 5. So here we have 2x minus 1 equals natural log of 5. I'm going to add 1 to both sides, and we will have 2x equals 1 plus the natural log of 5. So I'm drawing an arrow here from this line upwards to the upper right hand side of this section, and I'm writing 2x equals 1 plus the natural log of 5. I'm dividing both sides by 2. The 2's will divide out on the left hand side of the equal sign, and we'll be left with x equals 1 plus the natural log of 5 all over 2. And we're going to box that in. That's our exact answer. I'm also going to write this as an approximation. This is going to be x is approximately equal to 1.305, and I'm going to box that in as well. So the bottom answer here, the 1.305, that represents our solution as an approximation. And then the upper box, or the upper answer here, represents my solution as an exact answer. So I have written the word approximation underneath the x is approximately equal to the 1.305, and I have written the words exact answer above the x equals 1 plus the natural log of 5 all over 2. And I am circling the equal sign and the approximation sign just so that you realize the difference between these two answers. I am going to draw a vertical line segment. Separate the work from example 9 and 10 here. Let's go to number 10. Number 10 says 4 times e raised to the negative 3x power plus 7. And this plus 7 is not in the power anymore. It is down in the base level. So this is going to be equal to 55. So we've got 4e raised to the negative 3x power. And then we have separate here plus 7 equals 55. I'm going to subtract 7 to both sides of the equation, and then we're going to be left here with 4 times e raised to the negative 3x power equals 48. I'm going to divide both sides by 4. The 4's will divide out on the left-hand side, and we will be left with e raised to the negative 3x power equals 12. Then I'm going to take the natural log of both sides. So the natural log of e raised to the negative 3x power equals the natural log of 12. Using the power rule, I can bring the negative 3x out in front of the log and multiply it. So I'm going to write negative 3x times the natural log of e equals the natural log of 12. This will give me negative 3x times 1 equals the natural log of 12. Negative 3x equals the natural log of 12. I can divide both sides by negative 3, so the negative 3's will divide out on the left-hand side, and we will be left with x equals negative natural log of 12 over 3. And I'm going to box that in. That represents my exact answer. Now let's use our calculators to come up with an approximation for this answer. My approximation is going to be x is approximately equal to negative 0.828, and I'm also going to box that answer in. Let's move on to number 11, but before we do, let's go ahead and draw a horizontal line segment separating the work from example number 9 and example number 11. I'm also going to extend the vertical line segment I had drawn earlier between example 9 and 10, and I'm going to bring it down right below where I had my answer, and then from there I'm going to draw a 90-degree angle and continue it to the right as a horizontal line segment. Number 11 says 2 raised to the x power minus 6 equals 37. Let me rewrite the problem. 2 raised to the x and then minus 6 down in the base equals 37. I'm going to add 6 to both sides, and now here the 6's are going to zero out on the left-hand side, and we'll be left with 2 raised to the x equals 43. I'm going to take the natural log of both sides, so I'm going to have the natural log of 2 raised to the x equals the natural log of 43. Now I can apply the power rule, and I can bring that exponent on the 2, that x, out in front and multiply it to the natural log of 2. So it's going to be x times the natural log of 2 equals the natural log of 43. I'm going to divide both sides by the natural log of 2, so the natural logs of 2 will divide out on the left-hand side, and I will be left with x equals the natural log of 43 divided by the natural log of 2. That represents my exact answer. My approximation is going to be x is approximately equal to 5.426, and we're going to box that answer in.